Let's look at the second lesson in this unit, rates of change. What is rate of change? The velocity function, v of t, which is the first derivative function of the displacement. So you can write v of t as s prime t or ds over dt. This is just a Newton's notation. This is the Leibniz notation. Both of them represent the velocity function. The velocity function is the instantaneous rate of change in displacement with respect to time. So velocity is just a special rate of change. Not all the rates of change have a particular or special term. Therefore, rates of change is a more generic term for all the instantaneous rate of change. The rate of change is the first derivative of a function, or you can say f prime x or just dy over dx. It's the gradient of the tangent to y equals f of x at the given point. Dy over dx or f prime x is the rate of change in y with respect to x. So the rate of a change is just f prime x or dy over dx. If you do have the gradient of the tangent at a particular point, then you just plug this x value into the first derivative function to find the particular gradient of the tangent to the curve at that point. I also hope that you can learn some important skills, knowledge from the examples 3, 4, and 5 in the textbook yourself, and try the 4 examples in this lesson note as a self-practice to see how much you can apply the first derivative or second derivative in the real life contexts. Let's look at the first application of the first derivative and or the second derivative in the area of the biochemistry. Example 1. The quantity of a chemical in human skin which is responsible for its elasticity is given by this function. Q represents the quantity, T represents the time. So where T is the age of a person in years. Find Q at T equals 0 when the person is just born. T equals 25. Find the quantity when the person is 25 years old. T equals 100 years. Find the quantity when the person is 100 years old. B. At what rate is the quantity of the chemical changing at the age of 25 years, 50 years, respectively? C. Show that the rate at which the skin loses the chemical is decreasing for all T is greater than 0. Let's look at how to find the quantity Q at different ages. When T equals 0, we just use 0 to replace the T in the quantity function. So quantity should be 100 minus 10 square root of 0. Square root of 0 is 0. 0 times 10 is still 0. So that's 100 units. So the quantity at a T equals 0 is 100 units. So the person has a full set of the elasticity at that time. When T equals 25, so Q should be 100 minus 10 square root of 25. So evaluate this result, that should be 50 units. When T equals 100, so Q should be 100 minus 10 square root of 100. So that would be 0 units. So look at when this person is 100 years old, you will see this quantity of this chemical loses completely at that age. Find the rate of change in the quantity of the chemical. So we need to find the first derivative of this function. So dq over dt equals the differentiation of 100 is 0. So the differentiation of negative 10, this one should be turned into t to the power 1/2. This one should be negative 10 times 1/2 t to the power of negative 1/2, which gives negative 5 t to the power of negative 1/2, which is the same as negative 5 over square root of t. So when t equals 25 years, the rate of change should be negative 5 over square root of 25. This is negative 1 unit per year. So when the person is 25 years old, the quantity of the chemical is decreasing at a speed of 1 unit per year. When the person is 50 years old, so this dq over dt should be negative 5 over square root of 50. This one is negative 1 over square root of 2 unit per year. So the chemical, or we can say the quantity of this chemical, is decreasing at 1 over root 2 unit per year. C. Show that the rate at which the skin loses the chemical. So this rate is decreasing for all t is greater than 0. So we know dq over dt is the rate of change. This includes the change. Even look at B. So dq over dt is negative 1 unit per year. But when we answer, the rate actually is decreasing at 1 unit per year. So what is the rate? The rate is just like the speed, which is the absolute value of the velocity. So this is the velocity. But we need to show the rate is decreasing. This rate looks like the speed. So we need to put the absolute value on the velocity function, which gives us 5 over square root of t. T is greater than 0. So right now we need to show this one is decreasing for all t is greater than 0. So how can we show this function is decreasing? We only need to find the derivative, the first derivative of this function. So dr over dt will be negative 5 over 2 t to the power of negative 3 over 2, which is negative 5 over 2t square root of t. So when t is greater than 0, this one is positive, this one is positive, but with this negative sign, this is always negative. Therefore, the rate at which the skin loses the chemical is decreasing for all t is greater than 0. So this is also the rate of decrease is decreasing for all t is greater than 0. Example 2 is the application of the rate of change in the area of finance or business. Siebel make denim jeans. The cost model for making X pairs per day is a polynomial function. So the cost versus the number of the pairs they can make every day is this function. So you need to know this domain of this function. X should be greater than or equal to 0. X is not all real numbers for this polynomial function in this particular context. So find the marginal cost. What is the marginal cost? Why do we need to know the marginal cost? But anyways, they use this notation to remind us, okay, the marginal cost function is just C prime X. So we look at this notation, we should be able to find C prime X easily. C prime X should be 0.0009x squared plus 0.04x, then plus $4 per pair. So you need to remember C prime X is the rate of change, dc over dx. B, find C prime 220. Based on this notation, I know what I need to do. C prime 220 means in the derivative function, in this first derivative function, I sub 220 in for x. So it should be 0.0009 times 220 squared plus 0.04 times 220 plus 4. So the result should be around $56.36 per pair. What does this one estimate? So right now, let's look at what is the marginal cost. In economics and finance, marginal cost is the change in the total cost that arises when the quantity produced has an increment by unit, one increment by unit. That is, it is the cost of producing one more unit of a good. So what is the marginal cost? The marginal cost is the cost of producing one more unit of this product. In general terms, marginal cost at each level of production includes any additional costs required to produce the next unit. So what is the marginal cost? The marginal cost is how much does it cost to produce one more pair of the jeans. So what does C prime 220 estimate? So this value estimates the cost of making the 221st pair of jeans. If 220 pairs of the jeans are currently being made. So that means this is the estimation on the cost if I want to produce one more pair of jeans after I produce 200 pairs of jeans. Okay, so right now let's look at a C. Find C221 minus C220. So C221 is the cost value when you produce 221 pairs of the jeans. Minus C220, this is the cost if you produce 220 pairs of jeans. So if you use your scientific calculator to help you, you will get a C221 is 7348.98 minus C220 is 7292.40. So the difference is around $56.58. What is this value? This value is the actual cost to make the actual pair of jeans. So from 220 to 221 pairs of jeans. So how much do you need to pay if you want to produce the 221st pair of jeans? So this is the actual cost you need to spend. Look at this actual cost is fairly close to the marginal cost. Let's continue to solve D. Find C double prime x and the value of x when C double prime x equals 0. What is the significance of this point? So let's find the second derivative function. Based on the first derivative function, the second derivative function should be 0.0018 x plus 0.04. So let this one equal 0. So x equals negative 0.04 over 0.0018. So this x value is around negative 22.2. But you can see this value doesn't fall within the domain. The domain of the cost function should be greater than or equal to 0. So this one is not in the domain. since we are not able to make negative quantity of the pairs of the genes. But based on the calculus knowledge, we should know this 0 of the second derivative should be either non-stationary inflection point, or you can have the local maximum or local minimum of the first derivative function, since the second derivative is the first derivative of the first derivative function. And look at the C prime x, which is a quadratic function with positive leading coefficient, so it should open upward. So this value should produce a local minimum of the C prime x. So local minimum is way on the left there, so it's negative 22.2. So on the right side of this x value, the function should be increasing since this quadratic function opens upward. So the significance of this point is, look at, so after negative 22.2, so your rate of change is always increasing, doesn't have a minimum value. So once you want to increase one more pair of genes, the rate of change in the cost is always increasing. Example 3 will show us the application of the rate of change in the population growth. Let's look at this example. The number of bees in a hive after T months is modeled by this function. Find the initial bee population in terms of C. Find the percentage increase in the population after 1 month. Is there a limit to the population size? If so, what is it? After 2 months, the bee population is 4,500. Find the original population size. Find B prime T and use it to explain why the population is increasing over time. Sketch the graph of this function. Let's look at this function right now. I think this function doesn't look like any function model we have already learned so far. This is a very famous function model, which is called logistic function. Logistic function is commonly used to model the population growth. Let's look at the logistic function in Wikipedia. So the function looks like this one. So you can read what does L represent, what does X0 represent, what does K represent yourself. So look at the curve of a logistic function. This function is increasing overall, right? But if you look at the rate of change, so if you find the first derivative function of this one, so the rate of change is increasing first, then decreasing afterwards. So you will see as x is getting larger and larger and larger, so this f of x value, y value, will level off. So even for the world population, you collect the data from the beginning of 1900 all the way to right now. So you will find the world population also follows a logistic regression. So this is a very good question for you guys to think about your mathematics IA as well. If you're interested in logistic function, you can research the logistic function on the website yourself. At this moment, let's just try to solve every single question one by one. So A, find the initial bee population. So initial bee population is when T equals 0. B of 0 should be C over 1 plus 0.5 e to the power of 0. So C over 1 plus 0.5 equals C over 1.5. So if you change 1.5 to a fraction, this one is the same as 2C over 3 B's. B, find the percentage increase in the population after 1 month. So let's find the population after 1 month. When T equals 1, the population, which is B of 1, should be C over 1 plus 0.5 e to the power of negative 1.73 times 1. This exponent is just negative 1.73. is around c over 1.089. You can use the scientific calculator to get to the value, the result for the denominator, 1.089 around. So it's around 0.919c. How can we find the percentage increase? So the percentage increase equals the new value, which is 0.919c, minus the initial value over the initial value times 100%. C can be cancelled out. So this fraction is the same as 0.919 minus 2/3 over 2/3. So times 100%, then it's around 37.8% increase. Think about how to solve question C. Is there a limit to the population size? What does that one mean? So this one means I need to look for the limit when t approaches positive infinity. When t is getting larger and larger, is there a limit to the population size? So what is the limit of b of t when t approaches infinity? So limit t approaches infinity, positive infinity, b of t is c over 1 plus 0.5 times e to the power negative 1.73t. I try to change this negative exponent to the positive exponent. So this one should be the same as 0.5 over e to the power of 1.73t. Try to apply the limit knowledge we introduced in chapter 14 or 17 for HL students. You should know when t is getting larger and larger positively, this one is approaching positive infinity. 0.5 over a positive infinity value, so this fraction should approach 0. C over 1 plus 0, so this value is approaching C. Is there a limit to the population size? Yes. If so, what is it? So the limit should be CBs. And later on you will know this y equals C also will become the horizontal asymptote if you graph this logistic function. Let's continue to look at D. After 2 months, the bee population is 4,500. So when t equals 2, b of 2 should be c over 1 plus 0.5 e to the power of negative 1.73 times 2. And this value is given right now, it's 4,500. So this one actually gives me an equation to look for C. So let's use the scientific calculator to get to the value of the denominator. So the denominator is approximately equal to 1.016 equals 4,500. So multiply both sides by 1.016. So C is approximately equal to 4570.7. Therefore, the original population size should be 2/3 C, and right now the C value is around 4570.7 times 2/3. It's approximately equal to 3,047 bees. So that's the initial value for the population of the bees based on this value given for the population after 2 months. Question E, find B prime T. Let's find B prime T. First, I will change the form of B of T to this form, since I want to avoid using the quotient rule. The quotient rule is always complex. So I change the denominator to the power of -1. In this case, I only need to apply the chain rule. So C times, bring the -1 to the front, then 1 plus 0.5 e to the power of negative 1.73t to the power of -2. then d the base, the inside. So when you differentiate the base, it should be 0.5 e to the power of negative 1.73t, then times negative 1.73. Let's simplify this form into 0.865. So what I will do is I calculated this value on the scientific calculator, and this is a negative value. With this negative 1, it becomes positive value. So 0.865, then c, then you still have e to the power of negative 1.73t. Divided by 1 plus 0.5 e to the power of negative 17.3t squared. Look at this simplified form for the b prime t. You know c is always positive, and this e to the power of negative 1.73t is always positive, and denominator is squared, must be positive. Therefore b prime t is positive for all t values on the domain t is greater than 0. Therefore b of t is increasing over time. Question F for this problem. Sketch the graph of b of t. So let's just use the c value based on question D. So we use question D to find the c value, which is approximately equal to 4,570.7. We use this value to help us graph this logistic function when t is greater than 0. Because usually we don't talk about the negative time values. So the initial value based on question D should be 3,047. So that's the initial value when t equals 0. So the y value when t equals 0 is here. And based on question E, we know this b of t should be increasing over time. So this graph should look like this one. And based on question C, we know y equals c. So c is around 4,571 is the horizontal asymptote. So this logistic function should be increasing and approach the horizontal asymptote but never cross over or touch the horizontal asymptote. If we use the graphing calculator to graph both of the left side and the right side of the y-axis, you will see the graph of a logistic function so clearly. This trend is the same as what we have seen on the Wikipedia. Example 4 is the application of rate of change in the area of trigonometry. Example 4, find exactly the rate of change in the area of triangle PQR as theta changes. So the theta can decrease or increase. So when the theta changes, the size of this triangle will change. Therefore, the area of this triangle changes as well. So we need to find the rate of change of the area of the triangle when the theta is 45 degrees. So need to remember, when we talk about the rate of change, when the angle is decreasing or increasing, this angle has to be in radians. So we need to change 45 degrees to pi over 4 radians first. So how can we find the area of a triangle? This is side angle side. We know if we want to find the area of a triangle, we can use 1/2 AB sine C. So AB sine C is two sides with one angle between. So right now we have two sides with one angle between. So 1/2 A is 6, B is 7, C is the theta. This one gives us 21 sine theta centimeter squared. So this is the area of the triangle versus the angle theta. Theta changes, the area changes accordingly. So what is the rate of change in the area of this triangle? So we need to find the first derivative of this area function with respect to theta. So dA over d theta the first derivative of this function should be 21 cosine theta when theta equals pi over 4. So the instantaneous rate of change at this moment, at this instant, should be 21 cosine pi over 4. Cosine pi over 4 is 1 over root 2. 21 times 1 over root 2 is 21 over root 2. Some of you guys want to change this one to 21 root 2 over 2. They are equivalent. So anyways, the rate of change in the area of the triangle at this instant should be 21 root 2 over 2 square centimeters per radian. So hope that you guys can practice your knowledge through doing those homework questions. This is the end of this lesson.